In this video, we're going to talk about the concept of degeneracy as it applies to the three-dimensional particle in a box in certain situations. So, for the 3D particle in a box, we showed that the energy levels depend on the three quantum numbers, nx, ny, and nz, one for each of the Cartesian directions in which the box exists. This equals a constant h squared over 8 times the mass of the particle. And this is going to be times quantum number in the n direction squared times the width of the box in the x direction squared. And then same thing for y times the width in its dimension. Same thing for z over the width squared in its dimension. So this leads to distinct solutions when we have different A, B, and C. The energy levels given any value of nx, ny, and nz will be different if A, B, and C are all different. But for certain special cases, like for example, if we have the case that A equals B equals C, all the dimensions are the same size, this would mean we would have the particle is in a cube. So for a particle in a cube, we end up with what we would call degeneracies, or different wave functions which have the same energy. So for this specific case of the particle being in a cube, the energy is then going to be h squared over 8m, and if we call it just a for our length dimension, the a is going to factor out because it'll be the same on every denominator, and then we just have nx squared plus ny squared plus nz squared. Okay, so now if you plug in the values for this case of, let's see, of E of 2, 1, 1, where nx equals 2, ny equals 1, nz equals 1, that'll be the case, that'll be the same energy as E1, 2, 1, where y equals 2 and the other ones are, ny equals 2 and the other ones are 1. And that's also the same as where nz equals 2 and the others are 1. So this is what is referred to as degeneracy. These are each different quantum states. They each have they're each different wave functions. Here the wave function is 2 signs in the x direction. Here it undergoes 2 cycles in the y. Here it undergoes 2 cycles in the z. But each of these has the same energy. So if we make ourselves a diagram here, and on this diagram we are going to graph the energy of our particle in units of h, not h bar, just h in this case. I'm going to graph the energy in units of h squared over 8ma squared. So let's fill our y-axis with solutions. Going to go up by units of 3, as we will see why shortly. So let's say 3, 6, 9, 12, 15, and 18. Okay, so if we set all three n's equal to 1, we'll get one solution. It's the 1, 1, 1 solution. And the energy will be 3 times h squared over 8ma squared. Just substitute in 1 for each of these. You'll see that this is definitely the case. Then, if we make one of them equal to 2, you're going to get a value of 6 h squared over 8ma squared. But that's also the case no matter which one you pick. So 1, 1, 2 is the same as 1, 2, 1 is the same as 1, 1, 2. So this is the 2, 1, 1 and all other degenerate states. It is said to have a degeneracy of 3. There are 3 states of equal energy. Then, if we set 2 of them equal to 2 and 1 equal to 1, we'll get them at 9. So this would be states like 2, 2, 1, 2, 1, 2, and 1, 2, 2. Then, if we set all 3 of them equal to 2, we'll get a situation where we are at 12 but there's only one state. There's only one way for them to all be 2. But then you'll also notice if we pick one of them to be 3 and the other two to be 1, then at 11 under there, we're going to get a triply degenerate state at 3, 1, 1. Then moving up, things also get more crowded as you go. Specifically at 14, we have the first 6-fold degenerate situation where we have 3, 2, 1. You'll find 6 different ways you can arrange 3, 2, 1, and there are 6 different states for that set of quantum numbers. So that's a very, very degenerate state. And then as you move up, things start getting more and more clustered together. As you get up to 17, 18, and 19, we have situations like 2, 2, 3, and 1, 1, 4 right on top of that. And then right on top of that is 1, 3, 3. So you can see, in contrast to the one-dimensional case where all the energy levels were getting quadratically spaced further apart, where this n-squared dependence was spacing the energy levels further and further out, for a three-dimensional case, as you go higher, you start getting these high degeneracies, and a lot of times many solutions start becoming very, very close in energy to each other. So the spectrum for a three-dimensional case would look quite different than the spectrum for a one-dimensional case, because there's a lot more variety in the differences between energy levels. So there'd be a lot more opportunities for a photon to be absorbed by this type of system, given that there are so many different values of energy jumps which are available.